you're going to hear all of it from me, but what this is a collection of slides from a workshop on community codes that we had run at University of Chicago in September 2012. And various people who are responsible for development and distribution of codes had come and given their perspective on what it takes to build a community code and what are the challenges they face. So we had invited all of them to come and give, and it would have been a lot nicer if you had heard these talks directly from these people, but for some reason or the other, most of them could not, these three at least, Brian, Cecilia, and Matt, could not make it, but they graciously agreed to let me use their slides. So I'm making the best of it. To give you a background, Brian O'Shea is the associated with the Enzo code. Enzo is a cosmology communication code for structure formation. Cecilia DeLuca is sort of the gatekeeper for the earth science modeling. I don't know what F stands for, but something to do with earth. Sorry? Framework. Earth science modeling framework. Matt Turk is involved with Enzo, but he also masterminded the development of a visualization and analysis platform called YT, which also in its own turn has become a community supported and used tool of sorts. An interesting thing to keep in mind is that Brian and Matt are consumers of their own code, in the sense they do not just develop their community codes, they also use them for doing science. Whereas mine and Cecilia's perspective is different in that we are primarily responsible for the development and maintenance of the code. We do not consume our own code. So in the first part of it, I'll talk about the development and funding models that have been seen in the scientific community for a while. Then I'll go on to the three codes, starting with Enzo, going on to ESMF. YT I'm leaving for the end, but then on Flash, and then tell you the summary of what appears to be the common thread running through the development and acceptance of these codes from the communities that they target. So how many of you have read the book by Eric Raymond, The Cathedral and the Bazaar? Right? So it's a very interesting take on the community development process. So according to him, the cathedral model is where the code is open source, it's available with each software release, but the software development is essentially done by a core group, and external contributions, if at all, are very carefully monitored, and they go through a process of vetting by your core group of developers. And he presents the Emacs and GCC as examples of central control models. And then there's the bazaar model, which basically he credits Linus Torvalds as having fostered, and that's the Linux model, whereby there is a distributed community of developers, and then there is a gatekeeping process involved that assures the quality of the software, but there isn't a central control model that and a central control core of group developing. Vast majority of the scientific codes, even those that have become community codes, fall into the cathedral model. There are many reasons that people give for following the cathedral model. Some of them are valid, and some of them are not so valid. One of the most frequently given reason is scientific codes are far too complex to be supported in the cathedral model. That's not true, because people who are planning to use these codes have to understand them, and the process of gatekeeping would still make sure that substandard code does not get into the code base. The other one is much more pervasive in the scientific community, and that is actually a big barrier to people releasing their codes and making them available to the community. Also is people, I believe, wrongly perceive the ownership of the code to be giving them a competitive advantage, in the sense that they think there is an IP involved in there. If they have a code that solves a certain class of problems and their competitors don't have it, then they have an edge. for all of those who have gone away from this model and embraced the model of open source, they actually see the advantages of sharing their code far outweigh the advantages of hanging on to the code and not letting others see it, not least of which is greater, I would say, belief in the robustness of the code, because more people have seen it, more people have exercised it, so it is known whether the code is good or bad. Otherwise, a closely held code is always somewhat suspect in terms of how much of verification, validation it has done, whether the results it's generating are reliable or not. And the second one is that once the code becomes readily available to the community, the components get added much more rapidly and you get a more powerful code, and therefore as Bob Lucas was saying the other day, you're only limited by your imagination in how you can use it and how you can extend it. But there are some valid reasons that basically make the cathedral model much more easy to manage for the scientific codes. The first one is that scientists tend to be driven by, I need to get my science results out and everything else is a distraction, and therefore the software engineering process is a distraction. And so, and they tend to be skeptical of it. This has been my experience at Flash as well. Anytime I got a new person in my group that had come from, that had done some scientific work and that was into the business of doing anything other than the CS-oriented parts of the Flash code, would be actually, in the beginning they'd say, why are you making me waste my time cleaning out my code? Why are you making me waste my time writing this much documentation? I can be so much more productive. I can have this much more of solver done if you would leave me alone. 6 months later, the same people would have changed their tune because they would have realized the value of sticking to the software engineering practices, the coding standards, and so on, because somewhere along the line they would have been forced to look at code written by somebody else. At which point in time, the fact that there was huge amount of documentation and and the code was understandable because you could tell what was the scope of the variables, what each variable was meant to do, it just made the job of walking through somebody else's code easier. So it's a short-term view that many people tend to take, and it is a useful exercise to try to get past this short-term view. The other parts by the cathedral model appears to work better is, and the most valid one in many sense, is that for the scientific codes, the user communities tend to be small. So I'm not talking about generic molecular dynamics code that tend to have large user communities, but astrophysics codes, for example, the users tend to be in hundreds at best, if not tens. And therefore, the community itself is small enough that a true bazaar model is kind of hard to imagine. And the other usual ones are the quality of the code is hard to maintain, and the financials, the things that are very challenging is scientific codes are typically supported by funding agencies like NSF, DoD, NASA, DOE, and just to generate support for gatekeeping of the code, to support FTEs that would just do nothing but maintain the code and gatekeep it and so on, is very difficult to justify when you're writing such grants. So without gatekeeping, of course, a community code is hard to maintain. And the other one is that with all of these grants, the reward structure is the number of papers published, the scientific impact, et cetera, but none of these codes can be maintained well without the support for personnel whose primary job is just to do things like run the verification and validation, to run things like verifying that the coding standards are maintained, the grunt work that needs to be done, and the reward structure doesn't permit that. The benefits of the bazaar model are that you have a large community of users and co-developers, and so the debugging almost goes in parallel because people will be exercising codes in completely different ways, sometimes unexpected ways. So the problems will be found much more quickly and they would be fixed much more quickly. It is also true that the more people that are looking at the code, the more creative ways of getting around bottlenecks and bugs can be found. any limits in the infrastructure, for example. So when people are designing infrastructure for a scientific software, ultimately what goes into the infrastructure design is the ways in which they can think of how the infrastructure is going to be used. And it's not possible for any person or any group of people to think of all exhaustive ways in which software and infrastructure might be used. It has repeatedly happened, for example, in Flash, where some user would come and say, okay, you guys allow us to do this, 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 and this. It would be really nice if you allowed us to do this also. And it isn't hard to do. We can easily fix that. But it didn't occur to us that someone might want to use the code in this way. So such kind of infrastructure limitations are also exposed much early. The capability addition is rapid. Your codes become more powerful. And you yourself will benefit from that, because now you can tackle problems which you couldn't before. An example of this is when Flash started doing high energy density physics simulations, the first thing that needed to be added to the code was a radiation module. So a flux limited radiation module was added to it. The next thing we knew, a whole bunch of users in astrophysics and structure formation community started to say, oh, this is a useful thing to have. We want to use it too. So can you make it possible for interfacing? So how do we go about using it? And before we knew, the parts of the code that we had developed for a completely different community were being used by our existing user base to do more complex problems, more multiphysics problems, right? So those kinds of benefits happen also. Realize the advantage of this kind of model is that the code design needs to be extensible, needs to be readily extensible, because users always want something more, something different. And it should be possible to do that. Code shouldn't be very hard. It should be flexible. Now, some of the strengths of the bazaar model can also become the pitfalls of the bazaar model. So a larger community of people, larger people exercising in many different ways, it becomes harder to reach a consensus about what the design ought to look like, what features ought to be added, because everyone's more interested in what they want done. The personalities clash. In fact, in all of these code projects that I've been directly or indirectly involved with, the development, the design, the solving of the bottlenecks is the easy part. The hard part is always the human interaction. The hardest part in design is sitting in a group and getting a group of, even a small group of 4 or 5 people to agree that this is the right design. That's where much of the energy and because different people want to do different things, the prioritization can become difficult. Gatekeeping can be challenging, and another big challenge is that verification and validation for scientific codes has its own peculiarities and its own challenges that is not very well understood yet. And so in a bazaar model, it becomes even more challenging. The orchestration of capability combination gets harder in physics, in scientific codes, because as opposed to the other software efforts that have been successful in using the bazaar model, it's because physics is what it is. If it refuses to play well together in your architecture, it's not going to play well. It's not that you can change physics to adjust to your architecture, it is that your architecture has to adjust to the physics. But whether you do the cathedral model or the bazaar model, the open source mode comes with benefits. The first and the foremost is, if you have an open source code, no one can pull the plug on you. No one can say that this code is no longer available for distribution or support, right? So you have the source code, you can use it and modify, and if I am the code developer of that code, then that benefit includes me, which means that if I want to use that code, no one can pull that plug on me either. People who are using the code, the users, don't have to pay, but they are expected to contribute in different ways, such as help in generate funding, pay back with the time and attention that you pay and what you give back. Because in terms of generating funding to develop codes or support codes, the stakeholders are important. Now, our experience has been that not all stakeholders are equal. So you can make cases about a very, very large user community, and that does not move the funding agencies. What moves the funding agencies is if you have vocal support from powerful users, people who influence the communities, people who are recognized and known. So that is much more useful. Like if a whole lot of people go up in arms and say, no, our research will suffer if this code dies, then the code gets support much more than just going and saying, look, 2,000 people use our code. That doesn't cut any ice. The thing that helps right up front in having an open source model is to have object-oriented design, where you have strong interfaces and encapsulation that are enforced by language or the build system, that allows users to quickly customize the code for their own use. And because the code is open source, the users, if they choose to, don't have to adhere to the interfaces that are provided by the core code developers. So it may be that the local version, their own working version, will become incompatible with the code at large, but that's a user's choice to make. So the development of scientific community codes can follow several different paths. The most common one in the past, roughly about more than 10 years ago, used to be that somebody wrote a piece of code that others in the group found to be useful, started using, went off to other institutions, took the code with them, their students and postdocs started using, and the code became widely available. I think the most successful code in that model that I am aware of, and I might be completely wrong, is Zeus that Mike Norman had created for the astrophysics community. In fact, in some sense, Zeus introduced the astrophysics community to the idea of a community code that can benefit others as well. Here, there was no focused effort to build the code. It sort of took a life of its own. There was no very little software process involved. And what ended up happening was that that code itself had a limited shelf life. That's not to say that Zeus is not in use even now. It is in use even now, but Zeus has given birth to, was the basis upon which Enzo was built, for example. And Enzo had paid some attention to the software engineering right from the beginning, so it has a much wider user base than Zeus ever did. The more sustained path, and this is the path that Enzo took after learning lessons from Zeus, is that enough like-minded people become interested in the code and they actually start paying attention to the engineering of the code. Make it extensible, make it easy to follow, make it easy to maintain, and pay some attention to the future code growth. So as the code grows, so does its community. And Enzo is a very typical example of that. This model is still relatively rare, and because of the way things are changing, at least in the United States, this model is the occurrences are increasing, but they still haven't reached the point where much of the scientific endeavor happens in this way. One of the desirable paths, one that Flash was fortunate enough to have, is that explicit funding is given by some funding agency to build a code for a target community. So in that kind of funding, there is an implied support for the design phase. And the outcome is expected to be long-lasting and well-engineered. This kind of a development is becoming increasingly harder. When it does work, the codes that come out of this kind of effort are more capable and longer lasting. Next, I will go on to the example of Enzo. And so we move on to Brian O'Shea's slides. Enzo started, like I said, as a successor to Zeus. And for the first few years of its existence, it was a closed source. So from 1996 till 2003, it was a closed source code held closely by the core group of developers. Nobody had access to it. March 2004, Enzo was released, Enzo 1.0. I was one of the early users of the code because, in many ways it was a competitor to Flash. The story was that the elliptic solver in Enzo was close to an order of magnitude faster than Flash. And so I was curious about it. So I was one of the first few to download Enzo. And boy, it was hard. Because the documentation was written by people. So because the code had not been exposed to users that were not directly connected with the development effort, the developers had internalized so much information about the code that was reflected in the documentations that somebody who came from outside, there were holes all over the place. You couldn't make sense of it. It took several iterations of backing and forthing with the developers group before I could get even the code even to build. To the credit of the group of developers, they took that lesson to heart and they started paying attention to what they started looking for things that that were obvious to them but would not be equally obvious to another user coming in from outside. So they've taken those lessons, the code has developed, and the Enzo community today is where there are 12 very active developers that are spread over 10 institutions. In addition to these very active developers, there are overall about another dozen or so contributors that do it more sporadically. The Enzo users mailing list has roughly about 20, and all of this information is at this point, I would say, nearly a year old because this is September 2012. Enzo is used a great deal in all of the national, all of the high-end computing for HPC facilities. The financial support comes from NSF, AST, the astrophysics division, the physics division, the OCI division, from NASA, and from DOE. And there is Enzo has given rise to this complementary community for YT, which is the analysis and visualization packet. The model in which the development of Enzo is supported is that all of its active developers and users, Enzo is the code where almost all of its developers are also its users, right? So when they write their scientific grant, in there, they always ask for a fraction of an FTE for the development and support. So bulk of the proposals that they write are for the scientific work, but within that, they also ask for resources for code support. And that, distributed across several institutions, succeeds in supporting the development of the code. Gets iffy at times, but works better than trying to explicitly raise funding for the development and support of the code. That just doesn't happen these days. So its development model is entirely distributed. There are a very small number of developers per institution. This is a code that uses a distributed repository for code maintenance as well as distribution. So it uses Mercurial, and it uses forks and pull requests to move features from the development branches to the main branch. Main branch is where the release goes out from. Because this is a distributed team of developers, almost all of the development discussion takes place on public mailing lists, which are then archived and can be searched for discussions in the past that happen, and Google Docs, and the meeting notes get mailed out. As I've been saying repeatedly, most of the developers are astrophysicists who are, in Brian's terms, scratching their own itch, which means that they have something they want to go after, and it needs the code capability, so they develop that code capability, and then they share it with the community. They do hold 1 to 2 workshops every year, so that's why the average comes out to 1.5 workshops per year. And then they have, when as a community they identify that there is a certain capability that many of them want and can use, then they have these what they call the code sprints, where there is a focused effort by a subset of the developers to just build that capability and add it into the code. So it all works on the basis of goodwill, in that we will put in our time and effort, and others also should put in their time and effort, so it's not burden on any one group of people, they just share the burden. So the impact has been that there is an enthusiastic and heavily involved community. Enzo is very widely known in astrophysics. In fact, in CETA, for example, Enzo is the code that has the highest number of CPU hours being used among in the resources. That's the Canadian Institute of Theoretical Astrophysics. Code is flexible and extensible, so in that sense it delivers very high amount of science per dollar. And it has been a model for other open source science developments, at least in the astrophysics code. The challenges, because of its distributed model, have been that there is no leader of the development process, which means that nobody has a veto power, so nobody can say, nobody is agreeing, I'm saying that this has happened and this will happen. There just is not such a person. So sometimes it can be extremely hard to reach consensus. It is also difficult to motivate people to do the boring but important infrastructure projects. So as I had said, that when you're operating in a community code model and in this form of distributed fashion, the hardest part the most time-consuming part and the most draining part is building the consensus and keeping the community together. So Brian's conclusions are that conversion of the code from closed source to open source has its technological and sociological challenges, but the people who are part of the Enzo collaboration feel that it has been worth it. It has enhanced their transparency, the robustness of the code, the reproducibility. There is a wider adoption because there is greater faith in the robustness of the code. So that was Enzo. Next we go to ESMF. And ESMF has a completely different model in which it developed, and it's a completely different community that it targets. And its gatekeeping model is also completely different from that of Enzo. So the vision of ESMF was to build Earth system so to provide a framework on which the Earth system models can be built, assembled, reconfigured, and interfaces and toolkits could be shared among various users, so that there would be a growing pool of Earth system components that would promote rapid transfer of knowledge, that people shouldn't be reinventing the wheel all over the place, that would lead to greater productivity for the science, that this would provide a cost-effective general framework for the community. So its evolution followed, like I said, a completely different path. And this, by the way, is the set of slides from Cecilia De Luca. NASA's Earth Science Technology Office wanted to have an Earth system modeling framework developed, and so they asked for solicitation. So this is a case of a funding agency deciding to fund the development of a framework for a target community. In the end, a multi-agency collaboration won the award, and the core development team got located at NCAR. The initial task for them was to build a framework that demonstrated feasibility, and the rest of the funding was contingent upon that. They did that by what they call the version 2R. Then they went to phase 2, which was 3 years later, and now they got new sponsors, and they formulated a multi-agency governance plan, and that actually still persists. So many new applications and requirements were brought into the project, and the framework was redesigned completely. And I will speak to this aspect of a community code development much more specifically and in more detail when I'm talking about Flash. And then in the phase 3, the core development team moved to NOAA, and basically the basic framework got completed, and now the focus is on increasing the adoption and community of interoperable codes. So the computational context is that it's a team of specialists distributed over many sites that contribute scientific and computational components to the overall modeling system. These components can exist at multiple levels. They can be individual processes, physical realms, or multi-model ensembles. Components have one requirement, that they need to be able to couple together, which means that they need to conform to the interfaces that are part of the framework, have interoperable data structures, but the data structures are not always entirely consistent, so there may be need for transformations of data from one model to another, because sometimes it just is, like I said, physics won't always play well. If physics will insist that this is the data structure better for, this is a decision that the designers have to make at the time of designing the model, whether in the end overall performance, what the trade-off here is the transformation more expensive, or is the loss in performance efficiency more expensive if you try to stick to a data structure that is better for another module? And this is a decision that individual users make and do their development accordingly. The code runs on tens of thousands of processors. This entire framework is still not very heavily using the GPU, so it's mostly CPU based. The modelers want a framework that actually doesn't put too much overhead on them, and they want to have bit reproducibility. But the provenance collection is a culture that is increasing in this community, and that's a good thing to happen. So ESMF framework architecture, there is this component layer which has the grid components and the coupler components. There is the field and grid layer. These are the low-level utilities. These are the external libraries. So vast majority of people that are contributing to the code base, the actual computational code, actually step in here. So all of this, ESMF framework, and this is where the user code comes in. This slide, the summary of features, I've basically included in the presentations for completeness, but this is just something that you can read for yourself if you're interested. The interesting things out of here is that it's a Fortran and C-based model components, which means that C and Fortran interoperate with each other. That's actually the least challenging of the language interoperabilities that come your way. It does support hybrid programming model, which means that it's MPI plus OpenMP. And the license is an open source license. And this is the list of major users of ESMF components. That's National Weather Service, NASA Atmospheric, et cetera, et cetera, et cetera. So the usage metrics, that is available at this website. At the time of this presentation, which was again September 2012, there were 4,500 registered downloads. The values of ESMF, it's a community-driven development, and it is community ownership, which means no one institution or no one individual owns the code. The project is completely open, and even the management, the code, and the information processes are completely open. The project has a commitment to globally distributed developers and customer base, and they follow the principles of simplicity, efficiency, and they're committed to user management. So what were some of their challenges in making this work, making distributed code development work, and how they have gone about solving it? They have an all-to-all communication pattern, which means that everybody has the information. So email lists are archived, where the development correspondence is always copied, which means that no two people are talking to each other without providing a copy to the mailing list. And this is a very important thing, because sometimes people think that it's a small matter. I don't need to spam everybody, so let me just ask this question of the specific person that can answer this question. Before you know, it develops into a full-fledged discussion, and all of a sudden that entire history of that discussion is lost to the archive. So this is something that, again, as Cecilia was telling us, that people initially complain about and rebel against, but pretty soon, a few months into the project, they begin to see the value of it, and so everything is copied and archived. There are minutes for all of the telecons that happen for discussions. There are repositories that are main and contributions, and daily publicly archived test results, monthly archived metrics, public archived trackers, et cetera, So one-to-one correspondence, IMing, et cetera, are completely discouraged. The governance includes a change review board, which means that from the key user communities, there are technical leads that participate in this. This is not led by the development team. So they set the schedules and expectations for what should be the future functionality enhancements, and for the internal as well as the public distribution. So this is an interesting question that came up during the workshop because of their governance model as to how do they do the gatekeeping. Because there is a centralized release in this case, even though it's a distributed development, the release happens from this core group of developers. So what they do is they maintain two repositories. One repository is where there is no restriction on a check-in to be done by any of the developers. Releases never happen from this repository. What they do is, when they decide that a particular capability that got added into the general repository needs to be added into the release, then they go through the vetting process for that particular capability. So some resources get allocated, it gets tested, it gets verified, it gets they make sure that it does not violate the interoperability, et cetera, and only then that capability gets transitioned from the general open repository to the release repository. So the details of this you would have to ask Cecilia. because I don't know exactly how they're doing. But the thing that I recollect from this discussion is that they are maintaining two different repositories, and they do not allow the general potentially beneath the quality commits to contaminate the release repository. And it is a non-trivial thing to do. I seem to remember that it had led to a great deal of discussion back and forth between the users, between the attendees and the speaker at that workshop also. And I'll be happy to provide you with her contact information. Okay. The part of their governance also that recognizes social and cultural factors as well as technical factors. So one of the things, this is a fact that will come up over and over again, is that all the people who are participating in the process, keeping the discussion civilized, keeping the discussion productive and focused is one of the biggest challenges that is there. And making people realize priority decisions based upon the resource realities is another very serious challenge. And this was an interesting observation she makes, is that sometimes when everyone is equally dissatisfied and is ready to move on, it's a big victory. And people, they reiterate over and over that informed criticism is the most useful thing, and that's actually very true in any code development project. The governance changes and evolves over the lifespan of the project. So the functions that their governance performs is prioritization of development tasks, deciding when to deliver a product, what should be contained in that product, support the users, encourage community participation, leverage contributions, provide a mechanism for feedback, and if necessary, modify the organization structure as needed. Coordinate and communicate at many levels. So this is how complex their governance structure looks like, and it's pretty, there are paths going. There's a code development team, there's a specification team, there's a change review board, there's an advisory board, there is a interagency working group. And I remember as I was listening to her talk and I was looking at all that, I was feeling extremely impressed that they have succeeded in making this happen within the framework of basically within the within the framework of a community code development. So these were the slides about ESMF and from Cecilia. Now I move on to the code that I'm most familiar with, and to a very great extent have been the part of the development of the whole software process of the code. So in some ways, Flash's model is similar to ESMF, but not quite. In other ways, it is similar to Enzo, but not quite. So Flash started as a part of an ASC Alliance program where the funding was for scientific simulation of codes, but one of the parts where NNSA was interested in finding if it would be possible to have multi-physics software development done under an academic environment, because the labs had been doing it, but such codes were pretty much non-existent in the academic community at that point. So that was an experiment that NNSA was interested in conducting. So right from the beginning, one of the mandates for the center, the ASC Flash Center, was to not only do the simulations, but also to release the code to make a public code available. Again, because this was a sustained development, funded development targeted at a user community, there was implied support for design and good software engineering practices. One of the, and the way this code was expected to be designed from day one was the same code would be used for running many different applications, which means right from the day one, it was pretty obvious that the need for multiple alternative implementations will be there in the code. The only commonality between these various applications that needed to run was that they were all involved with reactive flows. As soon as the code started, there were two diverging camps. There was one camp that and you know, software engineering, so this is the time frame of 1998-99, and scientific world was just beginning to wake up to software engineering practices that the commercial world had been using for a while. So things like design by contract, unit testing, etc., were beginning to make their way into the scientific world. And obviously, as in any project, there were people who were very enamored of these practices and they wanted to do the right software design. But then there were the scientists who wanted to use the code right away, right? Because they didn't see any point of any of that. They needed to do their science. And so in the beginning, the two parallel development tracks started. So one group of people started developing the framework, and the other group of people took 3 existing legacy codes, smashed them together, and started to run simulations with them, right? Soon, it turned out that there just weren't enough resources to sustain both the paths. And in any such situation where there's a confrontation between a long-term investment and a short-term result, immediate need, the short-term wins out. So obviously Camp 2 won out. So the whole design by contract, etc., 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 went out of the door, and Flash 1.6 was released with actually, let me go on to the next one. It's a Flash 1.6 was released with Prometheus for reactive hydrodynamics, with PARAMESH for adaptive mesh refinement, and locally developed nuclear reaction networks and a specialized equation of state. And basically, it was F77 style of programming. There were common blocks all over the place for data sharing. There were inconsistent data structures, and there were absolutely divergent coding practices. No one other than the original developers of the code could understand their codes. And for the record, the original equation of state for the degenerate matter still exists in Flash, and it is still indecipherable. It is still something that everybody turns their noses up and tries not to go into the internals of it at all. Anytime someone has had to, it has taken 3 months to decipher the code. Because it's complex physics-wise, and it's completely incomprehensible because it uses Fortran style of S1, S2, S3 variables. You have no clue as to what those variables stand for. A few architectural features happened, even the smashing together, because there was a need to run multiple different applications within the same framework. So the concept of multiple alternative implementations was brought in. The script was built which would configure the code by picking up the implementation that a particular application was interested in. And so this formed the beginning of the inheriting directory structure. This clearly was not going to be anything that anybody could readily contribute to. So once a working code became available to the scientists and their need did not remain so very urgent to have something with which they could do their work, attention was paid to actually architecting the code. And that gave rise to version 2, where the first, and at that time, what was in vogue in the software engineering world was a centralized database for all the data. No module owned its own data. All the data was owned by this central module called the database, and everybody that wanted any data needed to query the database and get the data back from that. It did many good things to the code. It, for example, eliminated the common blocks. All of the data got inventoried because someone had to manually transfer the ownership of data from individual routines and units to the central database. Different types of variables got identified, primary variables versus auxiliary variables, etc., etc. And some sense of what physics capabilities operate on what variables became generally known. So there was an inventory going on. At this point, what had been happening was, as people had been developing their codes, they'd been developing their tests. This always happens, that tests get developed along with the, I mean, you always have to invest in developing codes if you want to have a reliable code, if you want to have faith in your own code, right? So a whole bunch of tests had been collected, and this had already started happening in the development where check-ins from one person would break something for another person inadvertently, because the various pieces, there were many moving parts and they were supposed to play together. So at this point, the developers group realized that having a set of tests that ran on automatically on the code every so often would be a good idea. And that gave rise to the test suite, which then started to run on multiple platforms. And the group formed policies about monitoring the test suite. So in those days, the deal was that first thing everybody coming into work would do is to pull up the test suite results, see if they broke anything, and the expectation was that if they broke anything, they would try to fix it. When that didn't work, a capability was added in the test suite to send email to the suspect tests. I mean, people who were running the group got very creative about how to get attention from people and get response from people quickly. But other than this inventory of data, not much else changed in the architecture. And that wasn't enough. In fact, Flash 2 had a great deal of difficulty in getting accepted within the center. People continued to use 1.6 for nearly a year and a half after version 2 got released to the outside world. So then there was a transition to version 3, which is where which also happens to be the current architecture of the code. So the good things that had happened between version 1 and version 2 was the inheriting directory structure, the inheritance mechanism, the customization mechanism, some of which I talked about on Monday. We kept those from the earlier versions. And notice that I've switched from they to V because Flash version 3 is where I came into the Flash code, into the Flash Center. So the first thing that we did was to define the data scope so that we had absolutely come to this conclusion that the centralized database was not going to work, that it was a really bad idea. So the first thing to do was to arbitrate on data ownership, define the scope of the data in every part of the code, define naming conventions in such a way that looking at the variable name gave you a great deal of information about where it came from and what its role was in the code, differentiate between the API and the non-API functions of the unit. So the idea of null implementation had been in existence in Flash 2 also, but it did not define the API per se. And there was no way to distinguish between functions that had were part of what was the unit's interaction with outside of itself versus the functions that were internal to the unit. So that was the other thing we did, was differentiate between API and non-API. We formalized the unit architecture. So what you saw in the software architecture slides of Flash the other day was the formalization that was also done in the phase of Flash 3. We also resolved lateral dependencies for encapsulation, and that was the example I had given for the interaction between particles and grid unit, again in the architecture presentation on Monday. We also introduced the concept of subunits in the framework, and this was one of the most far-reaching things that we did, was to to include a built-in unit test framework that now exists across everywhere in the code. Now, the other interesting thing that one can learn from the history of Flash is how the transition played out differently between going from version 1 to 2 versus going from version 2 to 3. So when going to version 1 to 2, the bias at that time was that really the scientists ought to be in charge because the developers are clueless. So the scientists were in control all the time, all along. And what they mandated was that the development and production branches needed to stay synchronized, which means that a function that was a bridge between two units had to keep its interface as it was, And the new version of the code, whether its data structures were consistent with that interface or not, had to have an implementation whereby that would also work seamlessly. So the developers had to like go through severe contortions in order to keep that kind of backward compatibility going. What this did was, it did not allow many changes that were needed, many deeper changes that needed to happen, and in the end made code more inefficient or less efficient, whichever way you want to look at it. Hugely increased the development effort, and because this led to so much complexity, unnecessary complexity in the code, it put a very high barrier to entry for any new developer coming in. The outcome of it was that this code would, when it was built in optimization mode, the interprocedural analysis would not produce the same code, and the code would actually fail. Because you go through 04 and higher, semantics are not preserved. And in this case, some parts of the code were just coming out with an applied IPA where they were just giving wrong answers. So you had to turn off IPA, as a result of which the code was running up to 20% slower than Flash 1.6 was running. So the scientists just ignored Flash 2 and kept using Flash 1.6. The other bad outcome of that was the bugs, the inconsistencies, etc., of Flash 2 didn't get picked up very readily. So, like as I was saying, that ultimately the production in the center switched to Flash 2 roughly a year and a half after the code was released to public. And that too very grudgingly. I think it was pretty much the management saying that, the management of the center saying that it's time to stop supporting Flash 1.6, all development needs to happen in Flash 2, so switch to Flash 2. That's what happened. The transition to version 3 played out in a very different manner, because at this point in time, with Flash 2, the scientists had a functioning code that was actually delivering for them. And the lessons learned had been somewhat internalized, that you needed a design from scratch, that developers needed to be in control. And there were other factors within DOE and Flash Center that played out in this being the decision, but basically the development of Flash 3, the core group of developers were pretty much left alone to do their job in peace. So the way it operated was, there's a group of us who went into the design phase. The scientists pretty much stayed out on the periphery, and we would consult with them as we needed to, but they didn't try to dictate to us what we had to do. So we went through a proper design process, in the sense the first 6 months of this process, we did not put down any code that went into production. That was all prototyping, design, looking at the trade-offs in various components and so on. We made a conscious decision not to try to keep backward compatibility going, and we did not try to keep development synchronized with production. In fact, that was one of the first things that we negotiated, that we were not going to do this if we had to have the development synchronized with production. All the focus was in building a robust framework that would stand the test of users and time. And we were allowed to do this because there was no one waiting on us to finish this in a hurry, because they had their own code, they could use it. The other very important point to remember is that by this time, the developers that were involved in the process of designing Flash 3 had actually become familiar with the solvers and had internalized the vagaries of the solvers. So we sort of knew what design decisions would lead to bad performance, what design decisions are going to lead to a badly designed code. And that is a very important factor in any code development, is that people who are doing the framework design need to be comfortable with what the solvers do, what are the requirements from the code. They should be able to understand the language of the scientist, and yet be able to, and yet be coming in from the computer science side where they can do the good design. So the methodology we followed was we built the framework in isolation from the production code base. So we implemented the infrastructure units first, and that too with the homegrown uniform grid, which helped define the API and the data ownership. We built the unit test for the infrastructure before any physics was brought over. The most important piece of physics in Flash is the compressible hydrodynamics. So that was the first physics unit along with the ideal gas equation of state we brought over. And then we didn't bring over any capability in the code until we tested the hell out of the code. So we started creating the test suite infrastructure for it. We started stressing its scalability. We started stressing its production readiness and everything. Once we were satisfied that there were no more bugs left, then we brought over PARAMESH, because that brings in its own degree of freedom in terms of complexity when you have an AMR. Then all of this happened over about a year and a half. And at the end of this, we were very confident that the framework was robust and had been tested. Now, the other thing that went on is all through the design of the framework and testing with just a pure hydrodynamics simulations, we kept consulting with the scientists. We kept digging for what were their pet peeves with Flash 2 and Flash 1.6. The things that they thought could be done better, the things that they thought were compromising the accuracy of the solutions. Many of these things came out, and there were bugs reported by users. We paid attention to all of this in this first phase and fixed those things before we moved on to actually start to build the code as a whole. Question from Paul is, during that year and a half, how many people were involved in the development? The code group consisted of 5 people, but we hadn't been very lucky in our recruitment. So I would say that there were 3 developers who were productive and 1 graduate student. So it was 3.5. Okay, this is the situation. The graduate student was actually, his thesis was not connected to Flash at all. He was in the state where, the department was not going to support him, so he needed to look for outside funding. And so what he was doing for Flash had no bearing whatsoever on his thesis work. So he was that good. He was really that good. So we really literally just got him for 15 hours a week. No implication on the student himself. We just got him for half-time. So once the code was that robust, we started to move the mature solvers over to Flash 3. Because here's the point. Point is that any simulation campaign that runs always has incremental changes happening to the code components that it's using. Sometimes they're slow, sometimes they're rapid, and the newer a module, the more likely it is to have many changes happening to it. So we thought that, the changes, picking up the solvers where these rapid changes were happening should be done at the end. So we started migrating the mature solvers over to the code base. And the agreement was that if someone made a change to the solver within Flash 2 that had already been migrated over to Flash 3, that they would consult with the code group, and they would make sure that the changes are synchronized. And this happened very rarely, because there were several code components that were pretty much left alone at this point. So we brought those over. Then we migrated the simplest production application with minimal amount of physics over, and the production for that application then switched over from 2 to 3. So notice the big significant difference is that we haven't even yet finished building the entire code, and already it was going into the production mode with whatever capabilities were available, because there was greater confidence in the robustness and the reliability of the code. And after that, what happened was, first application group started running with Flash 3, we thought the better alternative is to say, do it on an application by application basis. So whatever physics is needed for an application to transition over to Flash 3, we would bring that over. At this point, we stopped paying attention to the complexity, the rapidity of build, et cetera, et cetera, et cetera. We just brought over things that would enable people to switch over to Flash 3. What it did was, again, before we even released the alpha version of Flash to the world, it had been under production testing for more than 6 months. So the code was really fairly robust by the time it was released to the people. This was because there had been years of coexistence of the developers and the scientists. The other very important thing that happened, and I cannot emphasize the importance of that, is that the group of developers is all people with a very broad base, in the sense that all of us, not one of us had 2 degrees in the same field. Everybody had a bachelor's in one field and a master's or a PhD in another field. So some people had bachelor's in physics and a master's in CS. Some people had bachelor's in CS and then had gone and done physics in some way or another. I have a bachelor's in electrical engineering and a PhD in computer science. So this is how everybody in the code group was, which means that we could talk the language of the scientists without the scientists getting skeptical of our understanding. And there was this mutual trust had been built up. And there was much greater overall appreciation for software engineering and process within the center. The management had decided that this was worth investing into, and the code developers had the backing from the management to go about doing it this way. So the interdisciplinary interactions were still somewhat challenging, but it was recognized that they needed to be carefully handled. So there would be the teams that were represented from the developers as well as the scientist side that would sit down together and decide whether there should be what should be the trade-off between good long-term design and short-term science objectives, and so on and so forth. Now, this is the conclusion that I have personally come to, and many people may disagree with it, but this is based upon my experiences with Flash, is that both short-term science objectives and long-term design have their own place. Because it is true that there were several other efforts that started out with trying to build a framework for scientific codes, and several of them fell by the wayside because they were being developed by the people who are only computer scientists, who were not interacting with the science needs, and therefore had not really realized the ways in which these codes will be used. So they were really nicely designed frameworks, but they didn't really do anything for the scientists, and so they didn't get adopted. Flash, on the other hand, and this is both Flash and Enzo model, is that they started out by being codes that were capable of doing science and delivering science, and they got started, and then a structure was sort of coaxed out of them and built upon them, and therefore the framework was informed by actual needs of the solvers and developed organically. So, but at least once there is a usable code and the developers have become familiar with the code, at least once there needs to be a complete redesign step, and only then a good design will emerge for a code. And so a willingness to make wholesale changes to the code at least once is necessary. And I think actually it needs to happen more than once. For example, in Flash, one wholesale change was from 2 to 3 just to make the code maintainable and modular. I think the need for another wholesale change is upon us because of the changing hardware paradigm, where I think we need to rethink the architecture, we need to refactor the code so that it can deal with the heterogeneity that is coming our way. And I think doing it piecemeal, where you adopt every single unit to multiple architectures, is not the answer. We just have to rethink the whole code again, and that kind of willingness needs to be there from all application codes, as to rethink the whole thing, redo the whole thing from scratch when the situation warrants. Flash's management and governance model is it's licensed and distributed from the Flash Center. License allows modification and customization, but does not allow redistribution. The external contributions are welcome, but they go out and release go out as a part of the tarball that is released by the Flash Center. There is a newer model that people are experimenting with, and it's just come off online a few months ago, is that there are add-ons that people can host on their own websites, which means that those add-ons do not come with a user support from the Flash Center, but those add-ons interoperate with Flash, and users can download them as they need from their individual supporters. Flash's code group is a dedicated code group with many roles. It develops and maintains the code. It manages the production and project branches. If you remember, on Monday I had talked about how we make use of the way in which we orchestrate multiple simulation campaigns through the production and project branches. The code group also supports simulation campaigns at the center, in the sense that it helps design the Pathfinder runs. It helps in estimating the resources that will be needed to run a particular simulation campaign, and it is on hand because there's never any simulation campaign where some bug or the other doesn't show up at like 100,000 processors. So again, the code group has to step in to fix these problems. Sometimes there are in-flight optimizations because a particular component is taking longer than it should, and if you didn't fix it, the simulation is going to overrun its time. So all these problems keep coming up, and it's the job of the code group to also help support in all of those simulations. So the code group does not consume its own code, but it supports the consumption of the code. Building the community for Flash took several years, because for several years the entire astrophysics community was skeptical of this model where there was a targeted funding and there was a code to be generated, and people were saying that a code that tries to be everything to everyone is bound to fail. And there is some truth to that. Flash has avoided that pitfall by not building a single binary. So even though it's a code that has a lot of capabilities, it doesn't build all of those capabilities together, and that's what allows it to avoid that particular pitfall. In any case, the way community building happened was it all started with individual collaborations between members of the center and outsiders, so that outsiders would get the code, become familiar with it, start to use it. The alumni of the center took the culture and the code with them. Their students and postdocs adopted the code. Then we started holding tutorials on site and at scientific conferences, where we would have a hands-on session and help for user-specific problems. Flash distribution started including more and more example setups that people, and because of the customizability of the code, what happened was people would start with a setup that was in the distribution that was close enough to their problem, and then customize it for their own use. So their startup time became very low, and they started using the code. People started appreciating the availability of a robust infrastructure, I/O, and runtime, etc., that they did not have to manage for themselves. I think that contributed a great deal to the adoption of the code by the users. Once we started holding tutorials, and actually we ran a few surveys to find out how users were using and what they wanted, there were many surprising things that we found. For example, we found that several people used the code in their classroom as an example. So if they wanted the students to do something more than, say they were teaching a class in computational fluid dynamics, and they wanted their students to be exposed to more complex methods than what they could program for themselves, they would just use Flash. So they could demand more complex problems to be done by the students than it would have been feasible if the students had to code those problems themselves. One of the more surprising ones we found was this engineer from HP who would use Flash to test, because when he was swapping disks out, because if he did something wrong in his configuration, Flash would walk into it, and so that had become his test bed. There was one person who wanted to simulate a sailboat, but that was beyond the capabilities of the code. Within the community, we have a variety of user expertise, and all of those are supported. There are novice users who just execute one of the included applications, change only the runtime parameters, And you really can do a great deal with the available setups that are distributed with the code. Most users, however, go one step further. They will generate a new problem with initial conditions and parameters, and maybe sometimes write alternative API for specialized output, but not change any of the core capabilities. Then there are advanced users who take a look at what's available, look at what they need to do for themselves, and then build their own customized applications. The example you heard on Monday from Sean, where he leveraged quite a bit of the existing capabilities in the code, added some of his own, and has a completely different application working with the code. So I would call him one of the experts who actually started a new research field that got enabled by the Flash code, where he has completely new algorithms and capabilities. And many times people send the code they developed for their own purposes to be included in the code. And there are several reasons why people do it. Some because they're committed to the principles of open source, some because they think that because they're gaining something out of having much of the capabilities built for them, that they should give something in return. One of the most surprising ones was from a graduate student who wanted to contribute his code unit so his citation record would improve. So some of these slides are the slides that I sort of glossed over on Monday because there wasn't enough time, but I thought this is also the right context for talking about them. So the distribution policy is where there is a custom licensing agreement where the source code is included, can be modified, but cannot be redistributed. There are some parts of the code that are not distributed by the center, either because there are not robust enough tests available for them, or because somebody still subscribed to the principle of it gives me competitive advantage if I don't release the code. Once or twice a year there are full releases, and then patches are distributed in between. The contribution policies are, we balance the contributors and code distributor needs. So the contributors want their code to become part of the code because then it starts getting tested, and it gets, the big advantage to them is it gets, if there is any change to the API or the interface, their code automatically gets included in whatever updates are needed to be done. So it's maintained by the center. What we need minimum from the contributor is the source code, the build scripts, and at least one test that exercises that code and can be included in the test suite, and of course the documentation for the user's guide. We have an agreement on user support, and we always have a negotiated contribution and attribution policies. So code is accepted with the understanding that it will eventually be distributed. There is a pre-negotiated period of time when the code exists in Flash repository but is not released. So this is the payback from the contributor is that the code becomes part of the release. The support from the user, from the code developers, is that that for a while we support the user's code without getting any direct benefit from it. And the contribution needs to provide the makefile snippets and the appropriate tests, example setup for users. If there is an alternative implementation, then the documentation only for the code base is sufficient. If it's a new capability, then other things, for example, the equations that are getting solved, etc., for the user's guide are also needed. The attribution policy is that all of the contributions are acknowledged in the user's guide and release notes, and the contributors can also provide publications to be cited for the code. So the question has to do with the copyright, who owns the copyright, and how does the copyright operate in presence of multiple contributors from multiple institutions. The answer is copyright is owned by the University of Chicago. When the users contribute their code, the copyright does not extend to them. They can still distribute their own part of the code as they want, but anybody who downloads it as a part of the Flash tarball is then bound by the Flash license, where they can't redistribute it any further. And this is one thing on which we've gone back and forth with the university legal department for, I think, going on 2 years now, and still there isn't a convergence. One of the new things that we started doing as of last year was to provide a comprehensive publications page for all papers that either contribute to the code or do something with or use code in their research. and all users and contributors are encouraged to contribute to that publications, and that also increases their exposure, and it helps the Flash Center in being able to make the case for its impact on science. So for the community building, what did it take? What does it take? Popularizing the code alone does not build a community, right? Because then people take the code and go away, and there is no interaction, interchange of ideas, etc. The customizability also does not help very much. For example, the Flash Center's research priorities are rarely in alignment with what our users are using the code for. So what did it take? It took greater inclusivity, doing the tutorials, making it possible for people to come learn about the code, get their questions answered specifically, relaxing the redistribution policies, and providing huge amounts of user support. So the culture in the center is users are not an annoyance. Users are what we have the code for. Users are what provide us with any what you call the visibility, the whatever we need in order to make the case for continuing to be supported. The investment in robust and extensible infrastructure was very critical, because what happened with this, an example of a situation where this infrastructure has played an important role, for example, is that there is a group of people who decided that they wanted to use Flash for fluid structure interactions. And why did they decide they wanted to use Flash for fluid structure interactions? Because their algorithm is they use incompressible Navier-Stokes solvers, and then they use a method of least squares to move the solid body through the fluid, and they communicate the forces between the solid body and the fluid using Lagrangian markers. So Flash has a Lagrangian framework. Flash has, and they wanted to do it in adaptive mesh. Flash has a adaptive mesh framework. Flash has a multigrid solver that works on this adaptive mesh framework. It does I/O, etc., etc., etc. All they did was use the same elliptic solver to for incompressible Navier-Stokes solver using the pressure formulation, where you solve the pressure using multigrid, and they customized the Lagrangian framework a little bit, and they were able to build a completely new physics on the code where they do not use any of the solvers that come with Flash, not one, right, except for the multigrid, the physics solvers, that is. They just completely built their own physics solvers on the infrastructure that was available and went off and did a completely new application. So that robust and extensible infrastructure is extremely useful. And then, of course, the redistribution policies were somewhat relaxed in that we started allowing groups of people to use the code, and that also helped. But here's the common threads that run through all of these codes that I've talked about, is that all these codes are open source with a good governance structure in place. The governance structure varies from group to group, but it is in place, and basically all of the contributors agree to work within that governance structure. There needs to be trust building among teams. There should be a commitment to transparent communications and a strong commitment to user support. It takes either an interdisciplinary team or a group of people that are comfortable with both science and the code development practices to build robust community codes. There absolutely needs to be attention given to software engineering and documentation, and people have to understand the benefit of sharing as opposed to being secretive about the code. I think I'll stop now because this is time.